A 6,000 kilogram truck collides at right angles with a 2,000 kilogram car. The truck was going at 30 meters per second and the car was going 40 meters per second before the collision. Assuming the two vehicles stick together, how far did the wreckage slide if there was an overall coefficient of friction of 0.90 for it, that is the wreckage, and the pavement? So this is a fairly advanced kind of two-dimensional collision example. And it really involves kind of two processes. One of them is the collision itself, and then there is the kind of ensuing slide after that when the wreckage slides to a halt. And the way I'd like to approach this is to apply one area or one set of concepts from physics to the one process and a different set to the other process. Let me maybe start by drawing a picture here. So let's say here's like the truck. Maybe I'm taking like a top view here. So I don't know, here's like the front of the truck, whatever. Okay, so it's coming in with a velocity, and let's see, we said that was 30 meters per second, right? And then here's the car coming in, and it's going to get slammed by that truck, I guess, right? It's coming in at, I don't know if this is really drawn to scale or not, but 40 meters per second, right? It's 2,000 kilograms. The truck is 6,000 kilograms. So the way that I think about this is I'm going to say, hey, let's think about these as like 2-point objects, right? And they each have a certain amount of momentum. So maybe if the truck has an amount of momentum P1, the car can have an amount of momentum P2, but they're vectors, right? So this is an inelastic collision that's happening here. And the formula we have for the inelastic collision for the final velocity in vectors was this. And I made the claim that you could apply this in more than one dimension. I didn't really say how to do it though, right? And in this class, I'm not really expecting that people know how to plug into a vector equation. But given the picture I have over here with P1 and P2 vectors, maybe I could reinterpret this formula as being the vector sum of P1 plus P2 divided by the total mass. That's something that seems like a little bit easier for me to understand. And since I recognize that these two momenta are at right angles, if I were to draw like these two vectors, right? If I were to say, okay, like here is maybe, let's see, here is the P1 vector, and then we're adding to that it's probably smaller, I guess, right? Because that's for the car. P2 vector, the overall resultant vector that reflects the sum of those two, right, adding head to tail, would be this line right there. So that really represents that. I'm just going to draw a little line like this and say, okay, that part represents the P1 plus P2. And as a magnitude, right, what I could do is say, okay, since it's a right triangle, right, it would be P1 squared plus P2 squared is what I would find as a magnitude for, again, that part right there. Well, that's something I think I can do because if I look at like what is P1 that I'm going to square, since we said that was the truck, that'll be 6,000 kilograms times 30 meters per second. Then that's all going to have to be squared. I'm going to have to keep extending this line here. Okay, I don't know if that'll be long enough. P2, let's see, was 2,000 kilograms for the mass of the car times 40 meters per second squared. And that's something that then I could run into my calculator, right, if I wanted to. Although maybe before I go ahead and do that, let me recognize that the thing I'm actually after is this final velocity after the two of them have collided. And I'm really thinking about that not really as the final velocity, because this wreckage slides to a halt, but this is just the velocity right after the two of them have collided, but before they have slid very significantly. So maybe what I'd like to do is I'm going to say, before I calculate this, I'm just going to divide by the total mass, which is 8,000 kilograms. That reflects this division of m1 plus m2. But again, I'm just calculating kind of the magnitude of this whole thing as a vector with some geometry to guide me a little bit. I think I already said this was an advanced example, right? So I'm not necessarily expecting everyone in this class to do things like this on a regular basis, but it's kind of a cool example. Anywho, my calculator says about, let's see, it says like 24.622. Maybe I should be careful how much I round off here. Let's see, we're going to, I don't know, looks like we're shooting for just 2 sig figs or so. 1 or 2 perhaps. Maybe I'll say 2, even though it's a little ambiguous with the 30 and the 40 there. But I always like to keep a couple extras. So maybe if I just take this to 24.62, and that should be in meters per second if I track all those units through. That looks like a bit of a gnarly task to kind of go through all those units, so maybe we can just pretend and say we did, right? Anyway, 24.62 meters per second. The way I'm going to look at what this 24.62 meters per second is, like I said, is it's the final velocity for the collision, but that's really the initial velocity for the slide. And the thing that I kind of recall from looking at forces is if you have a coefficient of friction, right, and something is sliding, the acceleration on a level surface was simply equal, or maybe the deceleration, but I'm just going to say is equal to that coefficient of friction times g. I mean, maybe if you wanted to, you could say, oh, it's minus mu times g. I would say don't take that minus sign too seriously. If you want it, keep it. If you don't. I've put it there, though. Because the kinematic formula I think I can apply for this deceleration is to say that v final squared is equal to v naught squared plus 2a times a displacement we'll just call delta x. Now, this is the kind of generic version of the fourth timeless kinematic formula, and maybe I kind of deliberately kept this a plus here. I know it's a deceleration, so I could have made that a minus, but I already put this minus sign in here, so you kind of have a choice. Do you put the minus sign here or here? If you do both, it might get a little wonky, but anyways, I'm going to look at this, though, and say, well, okay, that final velocity goes to 0. This a I'm going to replace with that minus mu g, and so I think when I do that, I would wind up with the expression, well, let's see, I'd get 0 is equal to v naught squared, and if I maybe pull that minus sign out front, I'd get minus 2 mu g delta x, which, if I kind of move some things around the equal sign there, since they've got a difference of 2 things, I know those 2 things must be equal to each other, or moreover, I think I added something to both sides, but anyways, I'm thinking about it more simply than that. And I'd like to solve for delta x, right? Because that ultimately was the question there, right? It says, how far did the wreckage slide? So I'm interpreting that as looking for that delta x. So delta x would be equal to this v naught squared. Hopefully I've got all the numbers I need to plug in here, right? Because I think if I look at the downstairs stuff first, right, that would be 2 times 0.9 times 9.81 meters per second squared. If I'm not careful and I got lost somewhere, I might go look in the problem and start looking for what this v naught is. But wait a minute, that was what I already calculated. Even though here I called it kind of v final. Actually, did I even call it anything? I don't know. But that is the initial speed for this slide. So understanding that that is kind of my general picture of this situation, I'm just going to put that number in here for the v naught. Don't forget to square it, right? And then I'm going to put all of that into my calculator, and hopefully I've just got the tiniest bit of space there to state my answer. I get like 34.3, etc. But I think it would be reasonable here to just round that off to 34.3 meters. Barely have space for the meters there. So that's what it is, 34 meters, and that is indeed correct for this relatively advanced example.